In this lecture, I will discuss basically the concept of generalized method moment estimator. I will discuss how to get the instrument and how to derive the optimality property of the estimator. I will show that all the estimator can be interpreted as generalized method of moment estimator. And finally, I will discuss how to tackle the problem of identification using this GMM estimator. Good morning everybody. The topic that I will discuss today is generalized method of moments estimation. So let me start with the basic idea behind this generalized method of moments estimation. In general, method of moments estimation, sometimes called MOM for short, estimates population moments by corresponding sample moment. MOM is merely a proposal that to estimate a population moment or a function of population moments, use the corresponding sample moments or the function of the sample moment. Generalized method of moments GMM is a general method for performing estimation and inference. Now, most of the estimator discussed in the text are a special case of GMM. There has been an explosion of macroeconomic and microeconomic research using GMM estimator in the past decade, especially since the Hansen's seminal paper in 1982. In 1982, Hansen published a paper titled Large Sample Properties of Generalized Method of Moment Estimation, which appeared in Econometrics volume 50 in 1982. Now, there are mainly two reasons for the current popularity of GMM. First of all, GMM nets many common estimators and provides a useful for their comparison and evaluation. Secondly, GMM provides a simple alternative to other estimator, especially when it is difficult to write down the maximum likelihood estimator. That is, in many cases, we found that it is impossible to write down the likelihood function and hence the maximum likelihood estimator cannot be obtained. In these cases, GMM provides a simple alternative to other estimator. Now, the disadvantages are GMM is a large sample estimator, that is, the desirable property of the GMM are likely to be achieved only in very large samples. Typically, GMM estimators are asymptotically efficient in large cases but are rarely efficient in finite sample cases. That is, since this is a large estimator, large sample estimator, GMM estimators are asymptotically efficient in large sample but are rarely efficient in the small sample. Now, so let me start with the basic motivation. It uses the idea of population moments. For example, population moments, population mean of the disturbance term, that is expectation of the epsilon term is 0. From that, you can generate the sample mean, which is the simple average of the estimated value of the estimated residual. Now, second assumption that we use is the covariance between the x and the disturbance term is 0, that is x, the explanatory variable x is not correlated with the error term epsilon. This gives us that the covariance between x and epsilon hat, the estimated residual, is equal to 0. Now, let us take the simple regression model y equal to x beta plus epsilon. Now using the OLS estimate, you can get the estimated residual y minus x beta hat. Now in the next step, we will use the two population moment condition. First of all, expectation of epsilon equal to 0. This gives us the sample mean of the estimated residual is equal to 0. This is the sample counterpart of the population moment, expectation of epsilon equal to 0. And alternatively, we use the idea that the covariance between x and E is equal to 0, that is x prime multiplied by y minus x beta hat is equal to 0. Now using these two condition, that is one is expectation of epsilon equal to 0 and the other is expectation of x prime epsilon equal to 0, you get the condition x prime y equal minus x prime x multiplied by beta is equal to 0, and solving this equation you can get beta hat equal to x prime x inverse x prime y. This is nothing but the OLS estimate. So you can see that we can generate OLS estimate by using the concept of population moments and hence the sample moments, that is mean value of the estimated residual equal to 0 and the covariance between x prime and E is equal to 0. You get beta hat, the estimated value of the parameter is equal to x prime x inverse x prime y, which is nothing but the OLS estimate of the parameter beta hat. Thus you can see that the value of beta hat, which is equal to x prime x inverse x prime y, is nothing but the OLS estimate of the parameter. So one can conclude that OLS is a special case of this generalized method of moments estimation. Now in this case, you have assumed that covariance between x and epsilon equal to 0. But in reality, we may end up with the situation that covariance between x and E epsilon is not equal to 0. Now, using the condition that x prime covariance between x and E is not equal to 0, then you have to find out an instrument Z such that covariance between Z and E is equal to 0, that is expectation of epsilon E Z prime epsilon equal to 0 or Z prime y minus x beta hat is equal to 0. Using this condition, you can get z prime y minus z prime x beta iv equal to 0 or beta iv equal to z prime x inverse z prime y, that is the instrumental variable estimator of beta. So, using the condition that covariance between x and E is not equal to 0, we are searching another variable z satisfying the condition that expectation of z prime E equal to 0, and this gives us the condition z prime y minus x beta hat equal to 0, or you are getting beta hat iv as z prime x inverse z prime y, that is the instrumental variable estimator for beta. In other words, instrumental variable estimator for beta is a special case of GMM. That is, using the condition of population cross moment is equal to 0, you can get the condition that beta hat iv equal to z prime x whole inverse z prime y, that is the instrumental variable estimator for beta hat. Now in the previous case, while deriving the instrumental variable estimator, we have considered the case where the number of instrument is equal to number of coefficient that we want to estimate. The size of the instrument Z is same as that of the size of beta IV. Now, let me ask the following question: what happens if the number of instrument is greater than that of number of coefficient? Essentially, the number of equation is greater than the number of coefficient to be estimated. If this is so, then the model is over-identified. Now, maintain the moment condition same as before, and using that moment condition, you can generate the variance of Z prime E, which is nothing but sigma E square Z prime E, and let us denote the variance of Z prime epsilon as W. Now, in the next step, you can derive the suitable expression for that variance of the estimator Z prime E, which is a function of the variable W. Now, in the next step, we derive the expression for W by minimizing the value of the variance. Now, why do we carry out the minimization exercise? Because we have more equation than unknown. How to determine the true values of the coefficient? Solution is to minimize the previous expression so that the coefficients are able to approximate the moment condition, that is, peak coefficient is such that orthogonality condition get satisfied. Now, minimizing the expression V with respect to beta, you get and setting the value of the expression del V del beta hat equal to 0, you get x prime z transpose z inverse, z transpose multiplied by y minus x prime beta hat is equal to 0. And solving the condition, you get beta hat is equal to x transpose z multiplied by x transpose z inverse multiplied by x transpose z whole inverse x transpose z dash transpose z inverse z transpose y, and which is nothing but the expression for the two-stage least square estimator. In other words, you can see that instrumental variable estimator is also a special case of the generalized method of estimation. That is why in the beginning we have already noted that all the possible type of estimator used in the test can be clubbed under this generalized method of moment estimator. That is, most of the estimator can be interpreted as the GMM estimator, and we have already seen that OLS can be interpreted as GMM, instrumental variable estimator can be interpreted as GMM. In the case where the number of instrument is same as that of the number of parameter to be estimated. But if in the contrary you get more instrument than that is required, then we can see that the expression of beta hat coincided with the two-stage least square estimator, that is, we have a case of over-identification. So, let us discuss the moment condition in some more detail. Now, let us note that the model used may be nonlinear, so you need to apply Euler equation, and it will imply model in levels, not in log. For example, you can have data on consumption, output, and the other first order condition. Now, both ad hoc and structural model may be nonlinear in parameter of interest of the system. Now, model may contain the unknown disturbance term. For example, you can have rational expectation model, or you may be interested in studying the related parameter. So, let us start that you have some kind of a nonlinear moment condition. that is, you consider expectation of the m variable, which is a function of the explanatory variable x and the parameter beta, and the m function may be nonlinear in nature, and you are taking into account the covariance between the m function and the instrument z. So you are using expectation of m of x beta prime multiplied by zt is equal to 0. So this is of course a population counterpart. Now using the sample counterpart, you get 1 by t sigma running from t equal to 1 to t m of xt plus I times beta prime zt equal to 0. So these conditions gives you the sample moment condition. Now let us again use the minimization of that quadratic function, where you minimizes summation of t running from 1 to t m of xt plus I beta prime zt whole prime w inverse sigma running from 1 to t m of xt plus I beta prime zt. Now let us note that if we have more instrument than that is required, then suppose you have L number of instrument available, but you want to solve only K number of parameters. Suppose you have more instrument L than the number of parameters to be solved, that is K, then we choose to minimize the sum of m x t plus I beta whole prime zt whole transpose w inverse t running from 1 to t m x t plus I beta prime zt. Now we have to determine the expression for the matrix W. So let me ask the question, what should be the matrix W looks like? Now let us note that the symmetric positive definite matrix W yields an consistent estimator of the parameter. However, it does not yield efficient estimate of the parameter. Now Hansen 1982 provides the necessary but not sufficient condition to obtain the asymptotically efficient estimates for the coefficient. Now appropriate weighing matrix according to Hansen will be W, which is basically the variance of sigma running from 1 to t m of xt plus I beta whole prime zt. That is, you are taking variance covariance matrix as a weighing matrix, Now, estimation of the minimized criteria can be used to test the validity of the instrument. We have already noted that you have more number of instrument L than that is required, that is the number of parameters to be solved, and hence you have the case of over identification. Now, in this case, one can use Hansen J statistics J, which is nothing but n times t running from 1 to capital T, that is the number of observation multiplied by t running from 1 to t m xt plus I beta whole transpose zt whole transpose w hat inverse t running from 1 to t m xt plus I beta prime zt. So, in order to obtain the value of j, you multiply the above expression by the total number of observation. Now let us then consider the test for the validity of instrument and consider the case of W. Now we have seen that since you have a more number of instruments than the number of parameters to be solved, the above expression is a chi-square distribution with L minus degree of freedom. So, what we can do, you can test whether the above expression follows a chi-square distribution with L minus k degrees of freedom. Now, if a suboptimal weighing matrix is used, Hansen J statistics does not apply. So, Hansen J statistics will be applied if and only if you consider the optimal weighing matrix. That is, the choice of the weighing matrix must be optimal in order to apply the Hansen J statistics, and Hansen J statistics is a chi-square Hansen J statistics follow a chi-square distribution with L minus k degrees of freedom, and it will not apply for a suboptimal weighing matrix. In this lecture, I have discussed the basic idea of generalized method of moment estimator. I have shown that all the estimator used in the text, like two-stage least square estimator, ordinary least square estimator, instrumental variable estimator, can be interpreted as an GMM estimator. We have further seen that in order to derive the expression of GMM estimator, the choice of the instrument and the choice of the weighing matrix is important. We have discussed how to derive the weighing matrix and the instrument in order to derive the expression for generalized method of moment estimator. In fact, in reality, you can have more instruments than required, and hence we have the case of over-identification. We have discussed under what condition we will be able to estimate the parameters of the equation using generalized method of moment if you have the case of over-identification. Finally, we have also discussed that in order to derive the expression for generalized method of moment estimator, the instrument not only be optimal but also be efficient as well. We have also discussed how to get the efficiency property of the instrument.